clear this board a little bit. We're going to come back to this coin question. There's two ways that you can deal with probabilities. You know what? I'm going to leave this up here. That's important. We can come back to that. There's two ways I like to think about probabilities. Empirically or theoretically. And theoretically, although cute and nice and fun and easy, is unrealistic. But I'm going to talk about it because we talked about it first. You guys actually gave me a theoretical probability before we even started. So there's a theoretical probability, and then there's what I call an empirical or an experimental probability. The reason I love this, I fell in love with it years ago. As soon as I learned how to use Excel, I realized what Excel could let me do. And I started doing these kinds of experimental simulations. They're called Monte Carlo simulations. If you have the unfortunate luck of having me for 243, not only will you hear the exact same jokes again, which you've heard all 3 or 4 times this term already, but I'm going to have you run Monte Carlo simulations in Excel constantly. And they're phenomenal. You can answer a question. For example, if you're sitting dealer's right, 3 seats dealer's right, playing Texas Hold'em and the river card is drawn, what's the chance you pull a flush? You cannot answer that question theoretically, but you can totally simulate it using a spreadsheet. So you do questions like that in my 243 class. It's amazingly, it's how they predict weather. It's how actuaries tell you how much you're going to pay for a premium in your insurance policies. All of that is tied back to what's called simulations. Get ahead of myself. Theoretical probabilities. The way you do theoretical probabilities is you balance with a fraction 2 things. You balance an event space over what's called a sample space. This is what I had you guys doing in your last project. When you guys were doing, I'm going to pull this down, this is in your way to sound, I apologize. In your last project, when I was asking you all those silly questions about flip a coin 4 times, list all the outcomes, guess on a multiple choice question 5 times, list all the possible outcomes, 3 drunk people walk into a room, pull coats, list all the outcomes. That's what this is right here. This sample space is a how many possible outcomes can exist. How many possible outcomes exist for an experiment. That's what that number is. And that's going to vary depending on your experiment. For the coin experiment, it's pretty straightforward. How many outcomes are there? 2. 2. Now, there's a key phrase that is not being indicated down there. There's a key phrase that's not being indicated down there, and the key phrase is equally likely. Outcomes. This only works when the outcomes are equally likely. Now, for a coin, is that a fair assumption to make? Yes, because that's the whole point of flipping a coin to decide things, yes? The whole point of flipping a coin to decide things is because heads and tails are equally likely, as we just saw. You should get heads roughly half the time. We're going to see that again momentarily using Excel. The problem with this is it doesn't work in reality, and I'll come back to why it doesn't work in reality in general. We'll come back to that momentarily. But I want to talk about what this event space is up here. This event space, this is how many things you're interested in. This is the number of outcomes you're interested. There we go. In. And that can change depending on what you're actually studying. If you're flipping a coin and trying to figure out the chance of getting heads, then you're interested in the one outcome that is getting heads. If you are interested in getting tails, then you are interested in the one outcome that's getting tails. Is that interesting? What I find also fascinating about our little experiment over here is we saw more runs of heads than tails, right? I saw one run. The one run of tails that really caught my attention was that one that Jordan had way up there in the top right. I see a lot more long runs of heads, yes? At least I think there are more long runs of heads. But overall, there are slightly fewer heads than tails. That's why you can't just look at the long ones. Our eyes are drawn to those because they're a pattern. Tails, 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 tails. Or as my son calls them, a pattern. I love that he's even looking for patterns right now. But the heads actually are underweighted in our experiment versus the tails. Interesting, yes? Micah?
That's weird.
That is weird, but it's completely believable. It just means there are more little packets of tails spread out. So for every packet of heads that's 9 long, there are 3 packets of 4 tails each, which sum up to 12, which outweigh the heads by 3. I mean, that's all it is. And this is the beauty of randomness. You can't predict it happening. See what I'm saying? See what I'm saying? All right, come back over here. Now, that's the theoretical probability. And that's great for things like rolling dice, flipping coins, pulling cards out of a deck. Fantastic, fantastic. We're going to do all that stuff over the next couple of days, today and Wednesday. We'll get into the messier stuff next week where we have to start betting on the results. That's theoretical. It unfortunately does fall down a little bit in the real world because not everything is equally likely. And this came to me very, very brazenly about 15 years ago. I was teaching this class, a class similar to this, back on the East Coast. And we were talking about things like getting hurt riding a bike, because I've been a bike commuter forever. Right? Been a bike commuter, ride my bike to work all the time. And they're like, my God, how could you ride your bike to work? And I said, well, I just do. I get on a bike and ride. Freddie Mercury. And they said, but there's such a high chance of being killed. And I'm like, well, what's the chance of being killed? And they said 50-50. I was like, well, what do you mean 50-50? Like, well, either die or you don't. And then I realized, I'm like, oh my God, they don't understand what equally likely means, or maybe they do and they try to apply it to everything. So I answered back, do you drive a car? Of course. Why? You're going to die half the time. And they were like, oh. And then walked away kind of like stunned, kind of like, seeing stars. But that's the idea, is that this only works when you can break down the sample space into equally likely events. Now sometimes you can. Sometimes you can. For example, in 244 we test the energy field, the human energy field. I've often heard of this thing, which I just learned about a couple of years ago, about touch therapy. It's kind of like acupuncture or massage or something like alternative medicine. But the practitioners don't touch your body. They hover your hands right above your body. And the belief is that it adjusts the human energy field that we all have. I knew nothing about it until 2 years ago. I said, we can test that. We can actually test to see if folks can perceive that. Non-practiced participants can sense the energy field. So we tested 10 times in 244. We had people float their hands above other folks' hands with their eyes closed, blindfolded. And we say, I have them ask a question. I say, above which of your hands is my hand? I have the people sitting with their hands down like this, and I have the subject, hands down, blindfolded, hands up. And the practitioner, or the experimenter, flips a coin to decide which hand, and then puts their hand either above their left or right. And the person has to feel the hand, using the energy field, not wind, not heat, just the energy field, and say, it's the left hand or the right hand. And we keep track of the results. Don't tell them right or wrong, just keep track. And then we compare that, the results they get, to what? What do you think? That is the actual. But to see if people can actually sense the energy field, you know what we compare it to? You should, because we just did it. Flipping a coin. Because if people can't sense the energy field, they're pretty much just going to be guessing. I don't know, right, I don't know, left. And they're probably going to guess pretty crappily randomly. But on average, they're going to guess 50% heads, 50% tails, 50% left, 50% right. What's interesting that I found is that I keep track of this over time. People on average do a little better than coin flipping when we run the experiment. And I can't explain why. I don't know if it's poor experimentation. It could be that when my students are putting their hands down, they're coming down too fast and pushing air, which then is perceived. Or it just could be that we're quantifiably identifying the energy field. I don't know. I don't know. That's the coolest part. I don't know what's happening, but I can see the results. So that's the beauty. The beauty is, when I flip a coin, I know there are 2 equal like outcomes. But when I ask somebody, can they sense the energy field? I have no idea how those are weighted. It's yes or no. I'm not saying it's not 2 outcomes, right or wrong, but you can't assume it's 50-50 anymore. Does that make sense? To kind of drive this point home, I built coins years ago, which I can't find. They might have gotten lost in the move to Grandview. Somebody asked, well, when you flip a nickel, it could actually land side up on its edge. I said, that's good. It can it? It could end up side up, could land edge up. I've never seen it happen, but somebody claimed that it did. And I said, okay, well, even if it did, once, how many times would it happen? Once in how many, guys? What do you think? Make up a number.
1 in a million.
1 in 1,000, 1 in a million, 1 in 10,000, something very, very, very small, yes? So you flip a coin, it's either it's 1 in a million. 1 in a million, that means the heads and tails are roughly 50%, but just shy. It's like playing roulette at that point, isn't it? It's like playing the roulette wheel. Well, we'll analyze that too with craps next week. When you spin a roulette wheel, it's mostly red and mostly black, but the bastard casino puts 2 green spots on it. If you want better odds, go to England. They only have 1 green spot. Just so you know. But anyway, we'll analyze that too next week.
Does they replace that 1 green spot with the black or red?
No, but it's 1 less spot overall, which means the chance of black or red go up. Not as much as if you did that bench, but it still goes up. Good question.
So the average
Crap,
size.
I was going somewhere with that. Oh, so I had my dad build, he's an engineer on the East Coast, and he has access to CNC machines. I had him build me 3-sided coins. So it was as big as a quarter, a round, but it was taller. So what I was trying to do was I was trying to figure out how tall would a coin have to be until it was exactly 1/3, 1/3, 1/3. You see what I'm saying? So not half-half anymore. I want to put a third side on the coin. So I make it 1/3, 1/3, 1/3. And I still don't have an answer for that. Because the only way to figure out, I had to build me 5 different ones. 5 different ones. One's as tall as it is wide, one's half as tall, one's 1/4 as tall, a few other ones I messed around mathematically. The only way to figure out which one is closest to 1/3, 1/3, 1/3 is to do what? Start flipping. And that's it. And the trick with those is, I don't know how to flip them. With a coin, it's easy. You go like this, and they spin in the air, and that's random. If I do that with my 3-sided coins, I'm biasing against that third side. I'm spinning the 2 heads and tails, but I'm not spinning the third side. So I kind of invented this kind of like thing, where I kind of get it spinning randomly through the air, let it hit the ground. But the problem with that is, they start rolling. They'll hit the ground sometimes and start rolling, and then that biases against the heads and tails. So that jury's still out. The spinning biases it also against the heads and tails depending on how thick the coin is. The real thick coin, if I spin it, it never goes anywhere except stays on its edge. Yeah. And if you spin any coin, we'll cite this in 244, anytime you spin a coin, it's biased too. We'll come back to that in 244. Yeah, it's interesting. You're biased against one of the sides. But the point of the fact is that there are certain experiments that you cannot do this way because you can't count the sample space because you don't know the equally likelihood or lack thereof. So the other way is to do experiments empirically like this. So what you do is, you start by running an experiment. Experiment. And I'm going to put some mathematical, I'm going to put a mathematical symbol here. N arrow infinity. I'll bust a little calculus on your butt right here. I already made you do calculus this term. I don't know if you guys caught that or not. Did you catch what I made you do calculus earlier today? Or earlier today? Earlier this term? Instantaneous rate of change. When you were figuring out how fast I was on the bike. It was roughly commensurate when you stopped liking me. Roughly at the same time you were doing calculus. Yeah, when you were doing instantaneous rate of change, mathematically you were doing calculus. Pretty cool, huh? Pretty rad. So, here's a calculus phrase or notation. N is your number of trials of your experiment. Okay, it's the number of trials. Of course you have. Off to infinity.
As
Basically, as it approaches infinity, the probability you get from more and more and more trials is going to more closely resemble the perfect theoretical that you can't get. That's the thing. You can't always get this. You can get it with things like coins and dice and cards and things like that. You cannot get it in general with things like weather, for example. Weather. 80% chance of rain tomorrow. I'm making that up. I have no idea what the chance of rain is tomorrow. How do they know it's an 80% chance of rain tomorrow?
Last year.
They have databases of years and decades, if not centuries, of weather data. Centuries of weather data, yes, centuries, if not quite not centuries, but we just have decades. And they've known 80% of cases when the temperature is what it is, and the pressure is what it is, and the humidity is what it is, and the winds are what it is. 80% of the time it rained. So what they're able to do, we see all this? I think we can. Yes. What we're able to do once we get that is we create this fraction. We create this fraction. It's similar to this fraction, and you're going to see pretty closely how we have both of these over there. You're going to have the total number of trials in the bottom here. However many times you run it, total number of trials down there. Beautiful, beautiful.
And the number is the number of days since the National Weather Database was founded.
I'm assuming, or since the statistics have been held.
It was like 70 years ago, who knows?
I think that, well, the problem is you can get data from back before that. For example, I track bed snowfall data, which is, I got about 100 years worth of data on that. But that data comes from different sources. You can back stuff and collect data from different, it's called data mining, essentially. So you can get more even though it might predate some agency that collects it for us. But you keep the number of trials, what goes in the top? What do you think goes up top? Use ours as an example. I'll get you started. Number of times. What do you think? What? Say that again. Good. In this case, right? It rains. In general, number of times
That's the thing that you're
we see what we're looking for. I know, thrilling. It's the number of times we see what we're looking for, Micah.
So you could call it the number of times the event occurs.
The event occurs, using the language over here, the number of times the event occurs. I like that, that's good. Number of times the event occurs over the number of trials. And you end up getting, here's the deal, here's the beautiful part. There's this thing called the law of large numbers, LLN for short, that says these two things are going to equal each other as the number of trials increases. As the number of trials increases, those two things are going to equal each other. And the beauty of that is twofold. Number one, if we can theoretically discuss an experiment like this, we can get right to this and then see how that works out the same way. But think about it from a realistic point of view. The better part of this is the fact that if you can't get this, you can get it this way. And you can do this as long as you're clever about how you collect data. As long as you're clever about how you collect data. Does that kind of make sense-ish? That's a blowdown of probability. Real quick, I want to share something. I'm going to show you n going off to infinity, which is kind of fun. You're good, David, you're good. Let's recenter. Start.